artificial intelligence in 2026 looks nothing like the AI of 2018. Okay, let's just pause and think about that for a second. Let's dive right in. Just a few short years ago, we were celebrating because an algorithm could finally reliably identify a picture of a cat. Fast forward to today, AI has completely exploded out of that niche academic bubble. It is now a general-purpose substrate. It's literally powering how half the globe writes code, digs up information, drafts complex legal contracts, and yeah, even tutors our kids.
Welcome to today's Explainer. We're going to be breaking down a truly brilliant, comprehensive guide from Scixa on modern artificial intelligence. And look, our core thesis here is actually pretty simple. If you can deeply understand just a handful of foundational concepts, this entire modern AI stack stops feeling like some kind of dark magic and becomes perfectly clearly legible. So let's map out this territory together so you can start mastering the tools of the very near future. Here's our blueprint for today. We'll kick things off with the modern AI hierarchy. Then we'll look under the hood at neural networks and transformers. After that, we'll explore LLMs, RAG, and fine-tuning before getting into the really cool stuff, the rise of AI agents. Finally, we'll cover real-world applications, security, and wrap up with a concrete learning roadmap just for you.
All right, Section 1, the modern AI hierarchy.
The absolute biggest mistake I see newcomers make is treating all these AI buzzwords as if they mean the exact same thing. They don't. Think of the AI landscape like a set of nested Russian dolls or concentric circles. Artificial intelligence is the biggest, broadest category. It's just machines doing intelligent things. Think of IBM's Deep Blue playing chess back in the 90s. Inside that circle, we have machine learning, where systems actually learn from data instead of relying on hard-coded, line-by-line rules. Go a layer deeper and you hit deep learning, which uses multi-layered neural networks to find really complex patterns, like the famous AlexNet. And right there in the most complex innermost center, that's generative AI. It doesn't just categorize data, it actually creates entirely new content. And right at the beating heart of that center circle is the foundation model. These are massive, pre-trained models that act as a highly versatile base. Think of the heavy hitters like GPT-5, Gemini 3 Pro, or Llama 4. They are general purpose enough that they can be adapted to hundreds of different downstream tasks. Basically, they act as the bedrock for almost all modern generative applications you use today. Moving on to Section 2, neural networks and transformers. Now, to really grasp those foundation models, we have to pull back the curtain and look at the mathematical engine powering them. Stripped of all the sci-fi mystique, a neural network is essentially just a math function that you adjust using calculus. It basically boils down to 4 steps. First, a linear combination to weight the inputs. Second, an activation function, which handles all the messy, complex, nonlinear data of the real world. Third, a loss function. This just measures how wrong a prediction is. And finally, gradient descent, which gently nudges the parameters to minimize that error. It's kind of like having a billion microscopic sieves that just keep shifting around until the absolute perfect prediction falls out. But okay, the real turning point, that was the transformer architecture back in 2017. See, before this, models had to read text sequentially, word by word, which was painfully slow. Transformers completely changed the game. They convert text into numbers through a process called tokenization and then apply something called self-attention. By projecting queries, keys, and values, the model can actually look at every single word in a sentence simultaneously. This parallel processing is the absolute secret sauce. It's what allowed these models to scale up to trillions of tokens. Which brings us to Section 3, LLMs, RAG, and fine-tuning. So how exactly do we take that underlying math and customize it for real-world production? Well, a modern large language model is actually built on a 3-stage pipeline. Stage 1 is pre-training. This costs millions of dollars and involves the model predicting the next word across trillions of documents just to gain raw foundational knowledge. Stage 2 is supervised fine-tuning, where it learns specific formatting and tone from human experts. And Stage 3 is alignment, which uses human feedback to teach the model to prefer helpful and safe responses. Put simply, pre-training gives the model a brain, but alignment gives it manners.
But here's a massive question. What happens if that highly trained model doesn't know your company's private proprietary data? Enter RAG, or Retrieval Augmented Generation. I absolutely love this concept because it is literally the ultimate solution to AI hallucinations. Here's how it works. You ingest your private documents, chunk them up, and embed them into a vector database. When a user asks a question, the system retrieves only the most relevant data, injects it straight into the prompt, and generates a highly accurate answer with actual citations. It totally grounds the AI in reality.
Now listen closely, because a huge pitfall for developers is confusing RAG with fine-tuning, like LoRa. The trade-offs here are very distinct. You want to use RAG when you need to add fresh, inspectable knowledge to your model. On the flip side, use LoRa fine-tuning when you need to permanently alter the format or the tone of the output. But please, whatever you do, never reach for fine-tuning just to teach a model new facts. It is an incredibly expensive and brittle way to go about it.
All right, Section 4, the rise of AI agents.
We are currently in the middle of a massive shift. We're moving from standard LLMs that just sit there waiting for a prompt to stateful autonomous systems that can actually execute multi-step goals. These are AI agents, and they operate on a reason and act or react loop. They think, they make a plan, and then they take action. Crucially, they can now use external tools via the Model Context Protocol, meaning they can safely interface with their APIs. They observe the real-world results of their actions, and through a process called reflection, they self-critique their progress before deciding their very next move. This right here, this is the frontier of AI doing your busy work for you.
Let's zoom out a bit for Section 5, applications, security, and governance. These agentic and RAG architectures aren't just theory. They're actively reshaping industries today. In HR, we're seeing AI applied to internal talent mobility. It's matching current employees to open roles based on pure skill data, rather than arbitrary job titles. In finance, AI is reliably extracting unstructured data from wildly complex invoices and contracts, saving literally thousands of human hours. Over in education, systems like Khanmigo are providing one-on-one Socratic tutoring, which is historically the most effective way to learn. The big takeaway here is that AI is augmenting high-value human work. It's not about fully replacing human occupations. But we do have to look at the risks impartially, starting with some critical security realities. First off, beware of stuffing massive amounts of data into a single prompt. Models suffer from context degradation. They tend to get lost in the middle of all that text. You also absolutely must protect against prompt injection vulnerabilities. Legally speaking, complying with frameworks like the EU AI Act and NIST guidelines is completely non-negotiable. And most importantly, always implement a human in the loop for consequential actions. Deploying autonomous AI without human oversight in high-stakes environments is just a recipe for disaster.
Finally, Section 6, your AI learning roadmap.
Okay, we've covered a tremendous amount of ground today. If you are feeling inspired and ready to build, here is your concrete, step-by-step path to mastery. Step 1, start by mastering prompt engineering so you can get the absolute most out of the base model. Second, learn how to build a RAG pipeline to safely connect that model to your private data. Third, master the art of giving the model few-shot examples to guide its logic. Only then, as a fourth and final step, should you move on to fine-tuning open-weight models using LoRa. Trust me, if you follow this exact sequence, you'll save an incredible amount of time, headaches, and compute budget.
And that brings us to the end of our journey through the modern AI stack. We've gone all the way from the raw underlying math to fully autonomous agents. But the most exciting question isn't really what AI can do today, it's what you are going to build with it tomorrow, when these tools become as ubiquitous as the internet itself. If you want to explore these concepts in greater technical depth, read the complete guide on Scixa. Link in the description.